So today's speaker is Professor Dimitris Angelakis. Dimitris received his PhD in 2001 from Imperial College London. His PhD work was on theoretical quantum optics, and he was supervised by Professor Sir Peter Knight. Between 2001 and 2007, Dimitris held various fellowships and positions here at the University of Cambridge, and in 2007, he was awarded a professorship at the Technical University of Crete. Since 2012, he has held this professorship jointly with his role as the principal investigator at the Center for Quantum Technologies in Singapore. In 2018, Dimitris was awarded the Google Quantum Innovation Award, and he's a widely known person for his work on quantum optics and quantum simulations. And today, Dimitris is going to tell us about this work, predominantly on quantum supremacy and quantum machine learning. And I'm truly, truly excited and happy to welcome you here onto this quantum information seminar hosted by the Cavendish Laboratory and Hitachi Cambridge Laboratory. Thank you, Dimitris.
Thank you, David. Thank you, Crispin. Hello, everyone, colleagues, old friends from the old times in Cambridge. I wish I could be there in person, as we did 2 years ago, again in the Cavendish. That was my last trip outside Singapore, I have to say, December 2019, then COVID hit. We haven't been out since then, but things are softening up, so hopefully we'll be able to meet in person soon. Thank you for being here. Let me start sharing. I'm happy to take questions at the chat. I don't see you, so it's a bit like sailing in the dark, but I guess that's the way things are done now in Cambridge. It's much nicer to see the audience, but that's okay. I can see David, and he will be my audience. So please direct your questions to the chat, and he will pass it to me. So quantum supremacy and quantum machine learning with analog quantum simulators. What I will talk about is obviously not done by myself alone. There is a hard-working team of different people working in different areas. I will summarize 2 or 3 recent works, mainly done by Jiravat here, my PhD student and then postdoc. Now he has his own quantum computing company in Thailand. Then Supernut, another graduate student of mine, and also Mark, which was a postdoc and now also just recently moved on to back to his home country, Canada. Some of the work has been done with collaborations outside Singapore, some in Singapore. The one I will mention in the beginning is with the Google group and John Martinis, when it was still at Google some time ago. And I want to highlight that we have open postdoc and senior postdoc positions, also PhD students. There are also good PhD scholarships, but at the moment I'm mostly looking for postdoc positions. So if you are for postdoc people, if you are at that level, please write to me or go to this to our website and just email me. The main research threads that I'll be covering here are the ones in blue on analog quantum simulation and many-body physics. I'll say a few things that I kind of touched upon as well 2 years ago when I was speaking again in Cambridge. So apologies for the few minutes in the beginning that might be kind of a repetition for some of you, but maybe some others have not heard. Then I will spend most of the time in quantum machine learning with analog quantum systems and how you can actually use quantum systems at last and kind of convince the computer scientists that analog quantum many-body systems are supreme. I'll explain what I mean by that. This is something that a lot in the audience know what I mean in the sense of hard simulations, but the computer scientists have slightly different definitions, and we think we managed to bridge it now, and we have a proof that satisfies also the most kind of hardcore computer scientists that quantum many-body systems are hard to simulate. And if I have time, I'll talk about the more applied work, again, of course, basic science on quadratic optimization with NISQ processors and how we can bridge the gap between what is possible these days in terms of the number of qubits and the real number that is required for industrial applications. I won't touch 2 or 3 other areas that we actively work on these days, on topological systems, open quantum systems, and PDA and machine learning. I'm happy to talk later or next week if there's no time today. So analog quantum computing, I realized actually just today that the opening talk of this seminar series was done by Seth Lloyd on a recent work of his. This is slightly different. It's an analog quantum simulator perspective. And the idea is how we can use the available quantum systems and the dynamics without going into qubits or digital gates to do simulation and computing. And the motivation is that this is really friendly to NISQ devices. You can do more with less, basically. So let me just to slowly, mainly for the students in the audience as well, to define what I mean by quantum simulators. They're also kind of known now as NISQ quantum computers. The fields are coming in together. In the past, they were a little bit more separate. By quantum simulators, I mean controllable quantum systems, the real quantum systems, and this is very important as well. Now that the field is opening up, quite often I hear industry talks talking about quantum simulators as classical simulators. These are real quantum systems built by experimentalists, which they can be controlled at the lab, and they can actually verify or disprove a model we have for the behavior of real quantum materials, complex quantum systems that we cannot numerically simulate or do experiments on in the lab. So that's kind of the early definition, and also how Feynman brought it up into the field 40 years ago. There is a big variety of analog quantum simulators. The last 20 years, almost 30 years, since the Feynman's ideas. There are some early reviews here, and there are quite a few recent works. This I just went back a little bit in terms of early works here for cold atoms, for trapped ions, for conducting qubits. What I will say today applies to more or less all platforms, but the first 3 are the more relevant ones. And of course, what we call interacting photons, a lot of work we've been doing the last 10 years, also when I was in Cambridge, which basically goes under superconducting and possible polaritonic systems. So, and if you want to deep dive on that a little bit more, we're still active on that, although it's not the only research thread. You can have a look at this book we published recently with some collaborators of how you can use this strongly coupled light matter systems, photonic and polaritonic systems, to do quantum simulation. So the first part will be on quantum supremacy. So when I say quantum supremacy, probably is the most talked about term in the last year or so, since the Google experiments. I will try to tell you how we can use many-body systems, driven many-body systems, and how we can exploit the fact that they can, under certain conditions, thermalize and use the bit strings, the dynamics actually, to generate bit strings that are hard to sample from. And this is the kind of the heart of the proof, where it's merged concepts from thermalization, so this is physics, and computational complexity, this is information theory, to make this proof. The experimental implementation, we have done some simulations for different systems. You can think in terms of post-Hubbard models, or you can think in terms of Ising models, which are externally driven, and a lot of entanglement is generated. And then at some point, after a few cycles of driving, you start doing your measurements, you start sampling your strings, and then you see what I'll explain later in detail with these Porter-Thomas distributions, which was very similar to what Google observed in the random circuits. Before I go to that, let me talk about thermalization a bit, how all this came to us. It didn't just, I mean, there was a process to that. A few years ago, we motivated by the works in cold atoms, we tried to design an experiment using superconducting qubits where one could probe signatures of this many-body localization transition. Let me explain what I mean by that. There were a lot of works, including people in the audience, where many-body localization, that was around 2015, 2016, has been observed signatures, either the population imbalance or different aspects like many-body localization in the presence of dissipation, works by people in Munich and also by people now in Cambridge and Professor Snyder and so on, that have shown that it's quite hard to, when you do this experiment, let me just explain the experiment here for maybe the non-specialists in the group. You put your atoms in half of the lattice, you put a barrier, then you take off the barrier, you let them spread. There is disorder there, and the atoms try to expand. By trying to calculate the difference in the population between left and right, this is population imbalance, there are some oscillations, and at some point the theory cannot catch up. I mean, the experiment produces points that, you know, they're just too large of a system to do simulation. Now, this was known, and this is one example. There are many others where people, all the physicists or the analog kind of quantum simulator people, including our group, believe that this is an example of supremacy. However, the proof that this is hard to sample from was missing, and that's what we're doing here. Before we did that, we tried to reproduce some aspects of this experiment in superconducting qubits. Let me briefly revise what MBL and thermalization is, or what at least, I mean, it's a huge field by itself, but in the context of the talk today, in the thermalized phase, you have, imagine you have a many-body system. These are the states, the particles. When you have some disorder, when the disorder is small, the particles expand and they occupy all the space. Imagine 2 dimensions, or for example, like the previous experiment before, could be called atoms. As you increase the disorder, if the atoms are also interacting, some eigenstates start stay thermal, some other are localized. So the particles basically get trapped and they don't expand and they don't occupy the whole lattice. However, when that happens and what exactly is this transition and how we can probe it and predict what's going on is a very hard problem, because you need to access the entire spectrum. It's not like ground state phase transition, like what ferromagnet to antiferromagnet or other quantum phase transitions. So it's a very, very hard problem also for simulations. So one idea we had like 3 years ago was to take one of these precursors of the supremacy chips. This is 9 qubits now, there are 53 in superconducting qubits, motivated by earlier works we had in interacting photons for phase transitions. And we told the guys, why don't you tune your qubits away from their kind of qubit tuned regime? Because naturally, these guys are nonlinear oscillators, they have higher levels. So maybe they can behave as coupled nonlinear oscillators, where in the quantized regime, basically there will be some sort of many-body model, Bose-Hubbard-like. These are kind of effective photons that are hopping around here, and try to see whether we can see any signatures of this many-body physics that are seen in cold atoms and ions in that time. That was 4 years ago. There is a way to do that, and one can go back to the basic of CQQED, and in one case, in one specific technology, these are the transpons. They're different to each other, but the basic idea is the same. You have a Lagrangian. This is the kind of the kinetic part, and this is the Josephson energy. This is the flux. You can actually expand this term, and then you have this effective nonlinear inductance. This is the linear part. This is just a linear LC oscillator, and this is the nonlinear part. And you can basically show that if you go to the right regime, usually they try to tune these levels as non-linear as possible to have a good qubit. But you can actually, in certain realization, you can tune that non-linearity, this effective U, which is given. I don't want to go into details now, but it's given. It depends on the characteristics of the transmon or whatever you have here. This is a transmon, the Josephson energy, some other typical fabrication characteristics that have to do with the specific transmon technology, the charging energy, the Josephson energy. But the idea is that you can tune them. Typical values are, for this case, is 200 megahertz. The omega, the splitting is around 5 gigahertz, and the qubit lifetimes T1 and T2, the phase anticipation is around there. You could possibly, soften this up and have these other levels that in generally everybody's superconducting qubits try to avoid. You don't want to have any population here, to bring it closer, so you can actually, depending the coupling, if you have many of them together, depending how you couple them as well, there's different ways to couple them, to have some sort of hopping excitations, hopping interacting photons. That was our kind of picture, where this kind of photonic-like excitations can hop down the line and take this local attractive nonlinear oscillator. I mean, you can see this looks like one side in this Bose-Hubbard model, and then make it to a chain. And that's exactly what the guys did. They managed to fabricate that. And just to give you some rough value here, the U over J is around 3.5. And the omega is what I discussed earlier. This is at the microwave regime, and certain things can be tuned in and out with certain widths. So you have a Bose-Hubbard model. You have a Bose-Hubbard model. It is an attractive one, and you can send microwave excitations and flip and put particles in this lattice as kind of similar to cold atoms. There's a lot of physics here, as I mentioned in the book. There are a lot of discussions about chemical potential. What's the chemical potential here? Because of photons, how do they thermalize? I don't want to go into that so much. Just take at the moment that you have some sort of effective Bose-Hubbard model with bosonic excitations, photonic-like excitations that you can tune. And you can measure locally. You can measure locally, and you can measure X, Y, and Z, basically, when you go into this kind of spin picture and qubit picture. So can you use this setup to probe the kind of spreading of the states as you start playing with the interactions and the disorder, that the disorder can come either at this stir or at the coupling, depending how you do it. In our case, it was local disorder at the oscillators here at the omega, and they could tune the disorder to certain ranges, and then we could see how the states spread as that's happening. The way to do that was, there was what's called level spectroscopy method developed. The idea is kind of simple, it's based on normal quantum mechanics. You put some initial states that are not eigenstates in your lattice, and then you let it evolve, and then you make measurements. And from that, you can project your initial, your initial state that is not an eigenstate to the eigenstates, and from these coefficients, you can kind of reconstruct how your eigenstate looks like, what is its energy, but also how does it look in space. This is kind of simple quantum mechanics one type of idea. Of course, there's a lot of details behind it. You have to pick your observables in the right way. If you take any observable and you try to calculate the time evolution, you get energy differences. If you are looking for the energy spectrum, you have to do it cleverly so those energy differences are not there. And you also need to be able to, this is a simple example how to do that, how to pick up your observable that you measure in a clever way, so you get rid of this energy difference and get absolute energies. You have to kind of put a superposition in one of the sides, a 0 plus 1 and a 0 in the other, and then you let that evolve, and then you measure kind of quadratures. You don't measure kind of densities. You measure this, and this can be measured by measuring the sigma x and sigma y, the corresponding sigma x and sigma y for the single particle operators. It can be done, and they did it. This is for 9 qubits, of course, finite size system, small system. This is how it looks. You start, you flip one of your qubits. In this case, you flip qubit 2, you put it in a superposition, and then you let the thing evolve. There are oscillations, and these oscillations, it was 4 years ago, they last for up to maybe 500 nanoseconds, and before the system decoheres. Then you do a Fourier transform of it. You do it for different sites in your chain, and then you sum them all up, and then you can see from these Fourier amplitudes, you can reconstruct your eigenstates basically, and the positions tell you the energies. So you can then do a full kind of spectroscopy. Again, of course, this is finite size system for up to 2 or 3 particles. Maybe there are 100 or 200 eigenstates, and depending if your decoherence and your system coherence is large enough, so these lines are sharp enough and they are not overlapping, then you can distinguish them. In this case, you see this is one particle excitation sector, just flip one of this kind of oscillator, so qubits in this picture, and you get 9 sites, 9 eigenstates, because there are 9 sites. It's like the extended block mode in a sense. We benchmark that to do what's called the Hofstadter butterfly. There's some way to map this into this effective magnetic fields. This is one-dimensional model, but there is a mapping to 2D just to see how close we could get it. And it kind of, it was pretty accurate. The experimental error was up to 300 megahertz, it was up to maybe 13 megahertz, or maybe 5 to 10%. So that was reasonably good. They could get most of the eigenstates. This is the error. This is up to 15, and this is the total energy. There are some errors here at the head, but this has to do with the fabrication. So it kind of was a proof that can work for single particle eigenstates. And the same thing, you put 2 or you put 3 and you observe, and then you go to this many-body regime, where in this case now we plot exactly the extent of the states as a function. This is the lattice on the left. Vertically, we have the disorder over the hopping. If there was no interaction, you would have a flat area here. At 2, there is the specific model we were using has a phase transition at 2. Everything below 2 is low disorder, so it's extended, and everything above 2 should be localized. But now, because there is interaction, and interaction was 3 times the hopping, 3.5 times the hopping, this Bose-Hubbard type of model, you get this kind of edge, curved edge, or mobility edge, as it's called. It was very interesting to observe. This was another signature that this MBL is there, kind of complementing what people had seen in optical lattice with population imbalance and other signatures. And that was done in Google Labs. More recently, things like that, okay, with a 5-year, of course, delay, are being fabricated and built up here. These are some pictures of chips in experimental labs that are being now tested and tried. So hopefully soon we'll have this technology here as well and try some of these things. And let me move now to the supremacy things. So we have thermalization, we have localization. These are how to simulate phenomena in physics. Can we do something about really connecting them to what computer scientists mean by saying computational quantum supremacy? Just as a kind of a half joke, we want, if you do quantum supremacy, and Google says, you get like 8 million results, and there's a lot of random questions like, which country has quantum supremacy? Does the US have quantum supremacy? Why is it important, or is it risk? We mainly talk about the first one, although it's, just to show that there is a lot of discussion about this recently at different levels. So what I call the scientific kind of definition, with a pinch of salt as well, I call of quantum supremacy, I call it the story of the quantum monkey and the classical crocodile. So basically, people, many other fields outside quantum computing have been kind of chasing us for a long time, saying, but can you really do something that quantum classical computers cannot do? So smart people sat down and thought about it, and then basically came up with an idea, which is basically it's like having a monkey climbing a tree, and that's your quantum device, a very specific task, and your classical computer obviously cannot do it, but it's kind of a useless task as well, as useless as this silly example I'm showing you here. So the mathematical definition of these things are as following. So you are sampling, you have some random or complex quantum evolution, and given an instance of this evolution you should be able to construct a sampler C. Now we're switching from physics to more computational complexity terminology, but I'll try to keep it as simple as possible. Such that both output distributions are additively close. So if you could, this is a very well-defined task. This is now the monkey climbing the tree. There are many kind of definitions, but eventually people wanted to make something very specific that could be tested and proven that is hard in one case. So if your evolution, your quantum evolution is random, and then people prove that it's very hard to do that classically, to sample from that output distribution with a classical computer. So you have your quantum computer does a unitary evolution, but that unitary is random, okay? To construct a classical sample or sampler such that the output distributions are close enough up to additive error in this definition, the sum over all the bit strings, all the probabilities compared to of your classical sampler compared to the real distribution is close enough up to additive error, then you can do it. If not, then this is hard. So there are many proposals, early proposals for doing this kind of things. The one that Google followed was this random circuits. There's a different orthogonal, not orthogonal, but different approach using boson sampling and photons in waveguides and beam splitters. This is all linear optics. You put photons here. If you put many and you have enough waveguides, predicting where the photons will come out and where do they come out in twos or threes, and writing this whole transformation out and calculating the determinants is also a very hard problem. There was this another proposal on this instantaneous quantum polynomial circuits that also kind of satisfied this previous definition of how to sample from, and some other involving analog quantum hardware, however, not easily implementable proposals in 2D Ising models and 2D cluster state models. What Google did, they took this IQP kind of two approach where instead of having control Zs and local gates, you had a series of control not gates and local gates, but there was randomness. Each layer was basically randomly generated and implemented in the quantum machine, and the output distribution, if this was random enough, was satisfying or was proven to satisfy that condition. Now, that was the theory. Initially, the experiment, the theory was back in 2019, and then in 2019, the experiment happened with 53 qubits. What they showed that if you go deep enough in the circuit and you have enough qubits, then you can basically simulate that. It will take you, thousands of years or hundreds of years, or depending the algorithm you are using. That's also important because if you put more qubits, then the separation is exponential. So that was done, and a group in China kind of followed the boson sampling proposals, and a year or two later also kind of proved with a magnificent experiment of up to a teraphotonic people in the audience will understand the complexity of this work using linear optics setup, boson sampling type of setup, which up to 76 photons were detecting, and now I heard that they are even building it even higher. What we want to talk about here is how we use analog many-body systems, again, Bose-Hubbard models, Ising spins, as they come up in cold atoms or ions or other strongly interacting systems to do these kinds of things. Now, the way we approached it, connecting to this thermalization picture and MBL transition, is the following. We actually saw that if you take any of these Hamiltonians, let's say a Ising Hamiltonian or a Bose-Hubbard Hamiltonian, but now it's very important to have a drive. The drive in this case now, in the previous case, we did the static case on this early experiment. If you drive the system, that generates, if you drive it the right way, in this case, we have ZZ interactions, as you can see here, and magnetic field on the X. On the Bose-Hubbard, you have the nonlinear terms and you have hopping. Here we drive the hopping, and in this case, you drive the X, which doesn't commute. Whatever you drive to not commute with the rest in order to create enough entanglement to spread around. And then if you have disorder and you play with the interplay of the disorder to the interactions to the drive, you can actually generate random enough U's to satisfy this sampling condition. And what we first kind of calculated is if you take this many body system and you drive it for m cycles, m periods, so you on and off your couplings, you start from some initial condition, you on the coupling, you go up, you go down, you go up, you go down, maybe for 5-10 times, depending on how deep you want to go. You take your state, then you calculate the probabilities, you make measurements here. These are the bit strings and how the probability of measuring. Let's say these are 5 qubits in this case, or 5 spins. This is a Ising model calculation. And then you do the histogram of those probabilities. When you are in the thermalized phase, when the disorder over interactions and the drive, these are driven thermalized phases, the distribution of your bit streams follow the Porte-Thomas, which is exactly as the case for the random circuits that Google did. Here, this kind of circuits also generate the Porte-Thomas distribution, where in the hard to sample from regime. Of course, now this is an indication, okay? I mean, it's a very strong indication that the system will be, I mean, if the dynamics are very similar and the probabilities are Porte-Thomas, it will be hard to sample from. To go deeper in the proof, we had to kind of get 2 notions kind of cleared up. One is the notion that this U's that are being generated, the unitaries, the Floquet unitaries, because these are driven system, anti-concentrate. This is the terminology used in this scenarios. Basically means they spread in the Hilbert space in a certain way. This is the anti-concentration, and this is the concentrated case. If you have that, then the output bit string distribution will be Porte-Thomas. So unless you have this random matrix, the U is random, it will be hard to sample from. So that's kind of the connection. It's very important here that you need the drive for the proof. If you don't have the drive, you cannot show that your Floquet operators follow what's called the circular orthogonal ensemble of random matrix. This is early work by Leish and Riegel in 2014, which is a necessary ingredient for the randomness of the U as the randomness in the random circuits. Here, the randomness comes from this interplay of the drive to the disorder. And I won't go through the proof. I mean, it's very mathematical and so on, and parts are also, beyond done by collaborators. But the idea is you start from your driven analog system, you tune it to be in the thermalized regime that generates circular orthogonal ensemble type of dynamics, which in turn allow you to reach this Porte-Thomas distribution, which is a necessary criteria for the anti-concentration, which with the help of what is called the Stockmeyer theorem and an empty oracle can get you into this multiple, to do this collapse of the polynomial hierarchy if you could do it. So if you had a classical machine that could actually sample up to multiplicative error this distribution, that would be impossible. And then you have the collapse, and most people believe that this is not possible. So that in that case, this is supreme. So the key ingredients again is the drive and the disorder and the COE, the randomness of the unit matrix here. On the more experimental physics side of things, which most of us here in this audience are probably interested, what you have in mind, what's the background or the under the book here, you have some driven many-body system. It can be an Ising type of spin chain, or it can be a Bose-Hubbard model. You don't need local control. You don't have to do gates. You don't have to do digital approach. And still, you can probably now claim that if you reach this thermalized driven regime, that this is hard to sample from. And some simulation to back that up. This is the digital random circuits picture, and this is the analog, where you evolve this driven Hamiltonian into in periods. Then we calculate the distance of the output distribution to the Porte-Thomas. The Porte-Thomas is the thermal, the kind of the supreme regime, and PRP is what the system comes out, okay? So we want to get as close as possible to that Porte-Thomas. And you see that as you start basically your driving circles, your oscillations, if you do random circuits and digital gates, there is a trend to go down. As I saw in the Supremacy, you have to go up to 20 or 25 to claim you're close enough to the Porte-Thomas. These are small systems to see 7 qubits. However, if you do the analog, it goes faster and goes deeper because you generate more entanglement, like more randomness, basically. So you can achieve this kind of supremacy phase or regime with less cycles due to the effective long-range interactions that are generated by the drive. And you can also do level statistics. Again, this characterizes the thermal phase of the system and verify that you are indeed there, and that you have this Poisson versus circular orthogonal ensemble distribution. That's also verified. We ran those simulations and they fall as expected. And what comes as a bonus, and I will pause here for questions if there are any, that the phase of matter, thermal versus localized, is deeply connected to the hardness of sampling from it in terms of computational complexity. So if you are at the thermal phase, the dynamics of the system, this kind of quantum chaos type of dynamics, if you try to do a sampling experiment, that's very hard and hard in the supremacy context. So what I'm showing here, I'm showing phase diagrams. This is the disorder over the hopping, and this is the drive over the hopping. Here's the driven thermalized regime. This is the MBO, and this is the high frequency drive phase, which is a different phase. This is thermodynamics here on the left. This is the level spacing, level statistics. This is all thermal versus MBL in the driven case. On the middle graph, we see the distance to the Porte-Thomas. This is more like a computational complexly phased diagram. This is the Porte-Thomas. This is the regime where the bit strings are hard to kind of sample from, the sample of it. And you see that they're very, even by eye, they match very well. This is the driven one, and this is the Porte-Thomas, and they come, the behavior is there, even in this kind of finite size numerics. And a more experimental friendly quantity, because level statistics are hard to do, or even the Porte-Thomas is sometimes hard to generate and calculate in large scale experiments. If you calculate the entanglement entropy, you separate your system into subsystems and you do it many times and then you average. That also follows a very similar distribution. So I think I will stop here and take any questions before I change to machine learning, if there are any.
Okay, I think we have a question from Ulrich Snyder.
Okay.
And if anyone else has any questions, either raise your hand or write something in the Q&A section. Let's see.
Hey, Yuli. Good.
Hi, Dimitris. Great talk so far. Thank you very much. So, the way I understand it, for you to point that it is a driven system is an important ingredient to your proof.
Yes, for the proof. Yes.
You don't have the counter direction, right? So you would not say that a non-driven system cannot also show quantum supremacy.
No, we don't know that, but to do this proof, we had to go via this Regal and the COE thing, which is generated at the driven.
Yeah.
We are trying to see whether the CUE, I think if I get the terminology right, for the undriven is enough, but we haven't managed to prove it yet. But now this one at least works for this.
Because
for the machine learning I will talk about, that's not necessary. So in the machine learning is not that you can do machine learning with analog without being driven.
Yeah, but just to again, I mean, in some sense, what you do is with this drive and with this like having this huge spread of unitary, these anti-concentration measures, it just basically tells you about the amount of entanglement and thereby about entropy that you kind of create in your state.
Exactly. And that's what we see here in the entanglement entropy calculation as well. Yeah.
So can I then maybe take this around and make a very provocative and very simple idea, saying let me just take like a thermal state at a very high temperature. That is the state that maximizes all of those entropy measurements and thereby also all of those entanglement measurements in the many-body sense. Wouldn't then just sampling from a very hot thermal state already be a very hard complex problem?
Yes, that's exactly what our proof is about. Exactly. So that's exactly what this is about. That I skipped this part, that if you go to the infinite temperature regime, then it will be very hard to sample from.
Right. So basically, it just tells me that as an experimentalist, if I take my Coleton cloud and make it very hot, I do something that quantum
kind of, but the way you reach the U, it has to be the U. It's like it's the randomness in the U. So you have to kind of, as in the random circuit, you start from a very fixed state, a pure state in the random in the Google experiment, the random layers, right? And then you create this random. You have to be able to go everywhere in the Hilbert space, starting from one point. You need to have that kind of dynamics.
Yeah. If I would just take the thermal density matrix of a very hot state, it's got the same density matrix that I'm in the end sampling from, right?
Yes, but would that be quantum? That's the thing now. I don't know if because that's here we have this continuum thing that as in the that you start with something that's very quantum and you make it very random and it stays quantum and it's not kind of classical, because if you go to the classical, then all these things will have an issue.
Well, maybe that's the answer, right? That complexity just is like the new boundary for the quantum classical crossover.
Exactly. Like the always this boundary between classical and quantum world. There are very deep, interesting questions on this as well. But
indeed,
yeah.
Okay, thank you very much.
Thank you. So, any other?
I see that we have Mike Payne on the call now, and then we have some more questions in the chat here. So let's start with Mike.
Okay, yeah, I mean, thanks very much for this. I mean, the only thing I would still say is that you're talking about a number of qubits, which actually is fine on a classical computer. So I was really going to ask how much of your advantage is really down to timescales. So your classical computer, you basically is going as a gigaflop. So you're doing one time step, you're going to need a whole bunch over, all of your oscillations. So you must be getting, at least a millionfold speed up because you're actually doing it in the quantum system. I mean, I actually don't really understand why it's called a simulator. You have a quantum system and you're doing an experiment on it. It really has very little to do with quantum computing because you've just got great control over a quantum system and you're learning things from it. And to me, the biggest advantage at this number of qubit count, I mean, of course, that changes when you get to much larger numbers, is primarily actually the time scale rather than just the number of qubits.
What quantum computers can do, I'm not sure I fully understand the question, but let me take a guess. What quantum computers can do is they are not fast. This is the usual question. Sometimes we get also on the clock speed. Are quantum computers fast? The quantum computers are not that fast. It's just they do in fewer steps more things. You reduce the number of steps, but each step, which the time you implement that is slow, can do many more things. Now, so what we are doing here, we're saying instead of taking a series of digital, now there are two levels here. One is why quantum computers are fast compared to classical computers. I don't know if that's what you're asking, or why the analog, the normal, just natural Hamiltonian dynamics of a quantum system can generate these very complex states compared to the digital things. Which one are you? I'm not sure.
I mean, yeah, if you're talking about 5 qubits, I mean, that is not a huge number of states you need to explore.
Yeah, yes,
you
that's
can easily put
fine.
that on a quantum computer, and you can do tons and tons and tons of stuff with it because we've got lots of operations available. So I really want to distinguish how much of it is the size of the Hilbert space. The time it takes to do anything. Yeah.
Yes, the size. Okay. First of all, here we talk about not qubits but oscillators. So they are higher level. These are high level systems. So what we managed to kind of got these guys excited about, it was to tune their qubits that they used to do normal qubit and digital gates to this kind of what we call in the physics Bose-Hubbard models, higher level nonlinear oscillators that have many levels. The more levels you have, so supremacy here, or hard to access numerically, can take either, let's say hard to access numeric, which is more practical, can be achieved with smaller size. You don't need 54 qubits here or 54 sites to really get a massive Hilbert space. And especially if you have drive, what we are showing here in the simulations, even for like 20 sites with a drive, if you have enough excitations, you'll get to very, very complex states, even with 20 or 30 sites. But the key point is to be able to locally measure as well and do certain experiments to access that Hilbert space. The Hilbert space is massive when you allow more excitations and you allow the driving and this kind of massive entanglement that spreads everywhere.
Okay, thank you.
Thank you. Not sure if I answered your question, but happy to discuss.
I mean, at 20 qubits, yes, you're getting to quite large numbers. But I mean, some
imagine now 20
much smaller numbers. Yeah?
If you imagine 20 qubits with 10 levels each, let me put it this way: 20 n bits, 10 bits. I don't know how to call them, qubits, and then you have 4 or 5. If you have 10 of them with 10 levels and all interacting in the many-body sense, that gives you a massive Hilbert space.
Well, okay. So you're exploring that.
Yes.
Okay, not just the qubit, but actually a large number of states in each of those.
Exactly.
Okay, thank you.
All right.
Okay, I have 2 more questions. I'm going to read out here from the chat, Dimitris, if that's okay.
Just to highlight, I'm at 1/3 of the talk, but fine. I'm happy to discuss. I haven't talked about machine learning and I haven't talked about quadratic optimization, but anything fine. We can go either way. So
let's do these questions and then we'll go on.
Okay.
So I have a question from Georgia Nixon, who writes, "Hi Dimitris, I was wondering if you could reiterate the connection between long-range interactions and quantum supremacy. Yes. When you achieve long-range interactions, you are no longer simulating a usual nearest neighbor Bose-Hubbard model. What exactly are you simulating with long-range interactions?"
Yes, that's a very good question. This relates to the previous question by Professor Payne. If we have the drive, I don't have the slide here, but you can show that in the Ising. Let me see if I have the Hamiltonian somewhere here. In the Ising, instead of nearest neighbors, which is I and I plus 1, no, sorry, I don't have it. You can get I plus 2, I plus 3. Where is the, sorry, I lost the slide. Sorry, let me get the right slide. So here, yeah. So what is generally shown here schematically, it's I. Usually you have nearest neighbor, I with I plus 1, and then 2 with 3, 3 and 4. If you have the drive, this spin, these are spins in this case, but it could be Bose-Hubbard, talks to this guy and to this guy. So that allows you to generate entanglement in a massive way. And if the disorder is there, so entanglement is 1, but the other thing is that these guys are kind of fluctuating. We have disorder in each of them of a certain range. The total U, the total flow K U in this case becomes this segment orthogonal ensemble of random matrices, which is the key for supremacy. So you reach it much faster. If you don't have the drive, you don't get the COE, which is the necessary ingredient to have the anti-concentration and you know, generate this kind of collapse if you could sample from a classical machine. We don't know yet if we can prove it for the undriven. We're trying. We haven't managed yet. You need the COA to go to this. That's the key.
Okay, thanks. And then
now I see the question in the other. Yes, what exactly you simulate? You're simulating long-range Bose-Hubbard models, which are basically more entangled. That's the answer. Now I saw the question in itself. Yeah. Okay.
So yeah, and then there's the question in the Q&A here. So if I'm not mistaken, the Hubbard model, you assume a quantum harmonic oscillator for your wave function. Is that a problem for the higher energy states for your superconducting qubits when comparing experiments with theory?
Well, it would be different model. Now in the lowest approximation was an attractive Hubbard model. Now depending how you keep these terms and whether you have a transport or another thing, you might get weird other terms. So in the lowest approximation was just an attractive nonlinear harmonic oscillator Hamiltonian, which looks like a Bose-Hubbard. But you don't need to go much higher as well. We kept up to 0, 1, 2, up to 2 particles, because also the simulations are very hard to do for higher, and also the measurements, because the experimentalists know if you want to measure single and 2 particle subspaces or 3, then it gets more complicated.
Okay, thanks. Should we proceed, Dimitris?
Yes, let's move on to get into the QML part, which some you guys asked when you invited me. Sorry for keeping it later. I'll be fast. The idea now is we still stay at this analog many body systems, quantum systems, as they come in from nature and as they, you know, without having to put them in these boxes and to digitalize them and qubitize them, which is the way we think a computer scientist think, which is great. Algorithms are right, but maybe there's another way. And another indication that there might be another way to build efficient quantum learning machines is this paper we just published this year on how you can use, again, physics, localization versus thermalization, in this case, localization, to train the system in the Hilbert space to learn a target distribution. So you start from this initial, whatever is your initial state, and then there is a systematic way you can drive the system towards a distribution. This is what's called generative modeling. I'll explain it later. Somebody gives you a distribution you need to learn with your device. Could be a classical box or a quantum box. Once you learn the distribution, then you can sample from and make predictions. So how this works, again, there's no gates, there is no digital, there is no qubits here. You take your system, you initialize it in an initial state, you let it evolve. This theta, this is the kind of terminology used in this kind of machine learning. These are the parameters, which in our case are the couplings between your spins or the hoppings between your cold atoms and the disorder. You pick up one initial realization, you let it evolve, but the difference now to before is to the supremacy thing. You don't let it evolve for a long time and then you measure. When you reach here, you make a measurement after one iteration. Let's say you drive, you switch on your couplings and then you put it down like a cosine. Then you make a measurement, you see the distance of your state from what you can learn, and then you go back and you change your disorder and your coupling such that you have a classical optimization type of gradient descent or something to drive you there. So the picture here is kind of the more intuitive one. I start from here, then all this is the Hilbert space. This sphere corresponds to different states I can generate by starting from an initial state for different randomness different disorder realizations. So imagine there are a lot of points here. That's one. Now, each of them, I see how far they are from this state. If I take this state over here on the left, this is too far. This is not a good direction to go. It's this one. So I take this one and I generate another ball, and then another ball, and then another ball, and minimizing the cost function. I'll explain how now. Looking at the doing a machine learning type of training. What is the code in machine learning? You have a cost function, right? It's a cost function. Usually is a distance of what you have to where you want to go. In this case, the cost function is a physical quantity. Is again the KLD divergence. This how close to distributions are of your output quantum dynamics, and this is the P, what you generate, your best things that are generated by your quantum system, and the Q, which is the target distribution you want to learn. So using this as a cost function, this was kind of the first time that it was suggested. We can go back, so we do this, we do one round, we drive the system, we generate this, then we calculate the cost function and see at which direction of the couplings or the disorder I can go closer to where I want to go. So I go back, I change, and then I run it again. Then I go, I make some training loops here, I generate the next points in the sphere. Important here that you have to be MBL. Because if you're MBL in the Hilbert space, you're localized a certain, you don't go everywhere. If you are in the thermal phase, you cannot learn, because if you change, if you do this loop and you go back and you change the parameters a little bit, if there are VQE people in the audience that will understand what I mean. If you are in this kind of sensitive, chaotic thermal regime and you change the parameters, you just go somewhere very far. And the system cannot learn, there is no memory. That's why the physics, why we call it the phases of matter here. If you are at the MBL, the system can be trained and can be led to learn a distribution. And this is the numerics here. I mean, there's not all hand waving. This is real kind of numerics for this Ising or Bose-Hubbard models. If we look at this green area, which is over here, light green, you start from a cost function from initial state, could be whatever, some initial product state, and then you have to, let's say, to learn, in this case was a random Boltzmann distribution, a hard distribution, and you take the distance and they're very far apart. The cost function is 10 or 100. Then you switch on your interactions, you switch them off, you do that a few times for that set of parameters, and you calculate this next ball of states, and you see how far they are, and you see, now I know how to go down and generate the next parameters that drive me slowly as I keep doing this for 10 or 100 times. So it depends how close I want to go to this target distribution, how accurate I want to reproduce it. I can learn. The cost function goes down. When the cost function goes down, that means the system can be trained. In machine learning, there are two important quantities, the trainability and expressibility. Expressibility means your quantum machine or your classical machine should be able to be generic enough to learn very different distributions. And that's here is important that we be able to go to the whole Hilbert space. However, if you are very expressible, if you go to this kind of thermal more states, it's very difficult to learn because there is no memory. And that's exactly what we observed here from the numerics. If you start on the thermalized phases, you keep doing this protocol, but you just cannot learn because the system is too sensitive. In any change, you just kicked out of the learning direction as you go in. So what we how we see this is that this is specific numerics now for Ising models, but the same thing is for the Bose-Hubbards. You have your ZZ, you have your driving, and then you have your X, and you drive sinusoidally. If you don't have a drive and the disorder is small and you're in the thermalized, you have the thermalized phase. If you have large, you have the MBL phase. The system can learn in the MBL regime. You don't need the drive here. The drive is necessary for the supremacy, but not for the learning. If you drive it, you can also learn, but at different rates. So where is that next? Here, as we see here, the driven case, which is the driven is this one, and the MBL is this one. The dark green is the static case. It goes down as the driven. As long as it's MBL, remember you have to be in the balls. These are MBL, localized spheres or balls. You don't go everywhere. And in the thermal one, you never learn whether you're driven or undriven. The fact that you can you drive it, I think it has to do with again the entanglement here. You can go deeper and closer to the optimal distribution in this light green case, where in the dark green, in the static, you can still learn reasonably well, but then there is some sort of a plateau and a bit. Why does the cost function start to rise for large M? Yes, that's a very good. We don't know actually. It probably has to do with the entanglement generated there and the distribution you're learning. For this one, you stop when you're satisfied. I mean, as any machine learning problem, and depending on your numerics and how good your sampling is. Okay, let's. The question we have now open here, we hope to kind of answer in the future. There's two major bottlenecks in this quantum machine learning things. One is the data embedding, and the other one is the training issue, the barren plateaus. Okay, so the usual picture is you have your data embedding that ideally, I mean, there are many different ways. There is amplitude embedding. There is you can put it on your coefficients. However, those are very hard, and most of them require the existence of a quantum RAM, which is a very difficult thing. Then the next block is the trainable block. How good your trainable capabilities are in order to learn this cost function. Now, there are two major issues in the digital things, as I said, the barren plateaus, which is general variational VQE's issues. And what we hope to be able to do, and this is under evolution these days, in progress, is people have shown that if you use Hamiltonian encoding in your for some reason I can go back to the previous slides. If you go to your yes, or if you use, there are ways to encode your data using Hamiltonians. This is the recent papers by Maria Schuld and so on. So for example, you can use local independent magnetic fields, and this is just RZ, and this is your data. Now, depending the Hamiltonian you use to do your data encoding, you generate frequencies, and this is the expressibility part here. This is the function you want to kind of learn. This is the observable you measure, and these are the frequencies that are generated. You need to be able to have a lot of frequencies if you want to learn a lot of functions, basically. Lots of small omegas in this large omega capital space. Now, what people have kind of proven recently is that that you can choose, if you choose your encoding Hamiltonian in the right way, you have a lot of expressibility, and if your Hamiltonian, if your levels are not degenerate, that helps. But the best example for kind of non-degeneracy and disorder type of energies is exactly what we'll be discussing here. This kind of localization disorder Hamiltonians. So what we are trying to see to prove these days is how you go from this polynomial. These are, you have n frequencies and n expressible possibilities in this non-interacting regime. This is the polynomial regime. If you go to this chaotic, fully disordered interacting case, you have exponential, you have a lot of expressibility, you have a lot of frequencies. However, if you go there, it's very hard to train, and we've seen that with our our numerics, right? Because the system is too sensitive. Whether there is an in the intermittent regime where the interaction could actually, again, this kind of localization, this ball I was discussing about, can help you to balance trainability versus expressibility, and this is extremely exciting, at least to my opinion. So let me see. Any questions on this? I have a little bit to say on QUBO if people are interested. Otherwise, we can also call it.
So I think Jordan's question about classification and clustering. Let's see if we can get Jordan on the panel. Otherwise, I'll just read the question here.
I've seen it. What kind of learning problems can be solved with analog? Yes, classification or clustering. We have done, actually, I don't have the slides here. We've done kind of analog k-means type of stuff with industrial partners, where you can use this kind of hybrid approaches to do exactly this kind of things. Calculating inner products of vectors. That's exactly where we want to go. Whether you can do whatever people can do. Usually it's about vectors, inner products between vectors in some Hilbert spaces. Most of these algorithms is calculating distances between data, right? So this is definitely a very good question. Yeah. Another one? No. Okay. Let me close with one thing, because it's 8:10 here. It's Friday, and my dinner guests are coming 8:30. But happy to talk next week if people are interested. Quadratic optimization. Now, this is not analog. This is digital, but we found that there's a very kind of sensitive and misunderstood hype in QUBO, in quadratic optimization, in what we can do with quantum computers and what is really classical computers can do. Classical computers are very good. So I'll introduce what the problem of well, let me just briefly introduce QUBO for the non-specialists. In QUBO, you have basically travel salesman type of problems, max cut problems, graph coloring problems, and then you have a quadratic function, a cost function. You have binary vectors. You have A is your problem. In this case, could be let's say, where do you put your factors that generate energy in order to minimize the losses of transporting the energy and optimize your renewables and so on. Or you can have max cut type of problems. The whole point here, somebody gives you an A that can be quite large, can be up to 1,000 or 10,000 variables, and then you have to try all the possible bit strings, and which can grow exponential, as you can see, and find the one that minimizes this value for portfolio optimization, for many, many, many things. It's extremely hot and important in NISQ areas. Now, classical computers can do heuristically. I mean, these are huge spaces. You have 1,000 or 10,000 variables. You have 2 to the 10,000 bit strings to try. 2 to the 10,000 is a big number, okay? And even classical computers, very fast classical computers cannot do that. But with heuristic methods, they can do up to 10 or 15,000. That's where we are, called tabu sets and other things. Now, we claim in quantum that we can solve portfolio optimization, or we can do supply chain, and if you look at the number of qubits, and what we can do is maybe 20 or 25 or so on. So there's a huge gap here. So this cannot simply work. I mean, we have to come up with something different. And we think we have something different. That's what we just published as well this year. On a very simple, I will skip the background, how we do QUBO. I guess people might or might not be familiar, but very quickly what we do quantum annealing. That's the D-way. Basically, you take the rising Hamiltonian, you take your QUBO problem, you map it into spins, into magnets, and then you cool it down and you find the ground state. Or you do QAOA. This is Eddie Farhi and MIT stuff, very interesting, very successful in the sense that it broke the issues of going slow and not closing the gap. If you do QAA, you can get the ground state. You zap your spins in one direction, and the other is the interacting one you want to go, and you do that alternatively. But you can do it fast, and eventually you'll get the ground state. You don't have to go slow. Or you do VQAs, the hardware efficient VQAs, where you do this loop, and you hope you're gonna get there, but you have the barren plateaus and you have all the other issues here. However, all three suffer from the same problem. You need as many qubits as variables. You need there's also the connectivity problem, but I think the elephant in the room, at least according to me, is that you need 10,000 qubits to beat classical computers. 10,000 fully controllable logical qubits to really claim that we can do better than anything that the classical computers can do. So we need another way to encode the problem, and we came up with a very simple, this is extremely simple in conception idea, because there's some background into it, where if it works as follows. Let's say you have 8 variables, 8 0 and 1s here. Instead of having 8 qubits, which is kind of one variable, one classical spin, one quadratic cubo variable to one qubit, one spin, why don't I use 3 qubits, 0 0 0 all the way to 1 1? 3 qubits live in an 8-dimensional space, right? So maybe by using 3 qubits, 0 0 to 1 1, I can make the map of this cubo, of this quadratic lattice. In this case, this is this facility location, allocation, energy management type of problem. I don't need 8 qubits, I don't need 8 spins. I can actually enumerate them by using just 3, and I put one more here. We call this an ancilla, which tells me whether a facility, a factory, or an energy production should be put in this location or not. So if I do this simple mapping, suddenly I only need logarithmic number of qubits to encode my classical variables, okay? Log plus 1, log 2 plus 1. So I have massive compression, okay? So I could do 15 qubits for 10,000 variables. I mean, this would be great. Of course, this is, I mean, it's great, it is great. It is like mean field theory to keep you basically, just to spill the beans. It is like mean field theory for quadratic optimization problems. But quite often, mean field theory, as we know it from condensed matter and correlated, systems, works very well. And most of the time, a lot of things are done there. Now you can build on top of that and add correlations, classical correlations, because your factor is, if I put here and 7 and 8, maybe there is some correlation the way the problem is done. I can capture that by adding ancillas here. And we've done all these simulations, and I will end here. You can add this 2 ancillas now. So I have log 2 plus 2, and then I do my training as before. I don't have to do anything complicated. I do VQAs. It's hardware agnostic, and that's to cut all the details. We just compare it to the state of the art of Google QAA of 23 qubits. Google solved a few months ago 22 vertices max cut problem in 3 max cut, 3 connected or a fully connected, and they required 22 qubits. Then they had to do a few hundred of gates. In this case, they required 17. They could do up to 17 because this was fully connected. It was a harder problem. We could do this with 6 qubits only instead of 22. We didn't have to do 75 layers of 1 qubit gates. We could do it with maybe 30 gates. And we could get the same cost function and even better. So let me show you the numerics. So this is how the compressed kind of encoding variational algorithm has worked. The cost function goes down. But let's look here. How does it compare to the best out there, QAA by Google? So if you do 1 layer, you have 204 gates. And if you have, in our case, our minimal encoding, you only need 14 gates, and you can actually go lower even in the cost function. There's a question: how sensitive are you to the control fidelity that you have? We've done. This is the fidelity thing here. So we took state of the art, 99%, 99.9 or 99, F1 and F2. So the constant line, blue and gray, is the noisy with this, and the noise free is perfect case. So this is the circuit depth. So here is two layers of QAOA a la Google, 200 gates. And then it goes, as you increase the circuit depth, you see the noise free, you get a little bit lower in the cost function, you get a little bit better. In the noise case, you stay flat. For us, the minimal encoding is really good if you go down. Of course, if you have some noise, it is sensitive, but it's still much better than what Google do. And you only do 14 gates for L equals 2 instead of 200. That's this can be seen here for larger problems as well. 8 variables, 4 qubits, 32 variables, 6 qubits, and 64 variables, 7 qubits. Which, if you and I'm finishing with this, if you compare it to this is with two-body correlations. If you want to go deeper, you can basically do. You don't need 22 qubits to do 22 vertices. You can do it with 8, and if you have 22, you can do maybe hundreds or maybe 1,000 variables. That's the idea. We are working with industrial partners here to also with some startup. We are setting up to do some of these things in real world scenarios for shipping lanes and also in transaction settlement problems with the Singapore Stock Exchange. And thank you for your attention. I'll stop here and happy to take more questions.
Thanks a lot, Dimitris. Let's see, I can see that there's one question here in the chat from Charles Smith. He's asking, how sensitive are you to the control fidelity you have of your states? And I think this question appeared during your machine learning part of the talk.
It's the machine learning. I thought it was on the QUBO, and I saw that.
I might be mistaken. So maybe you could give us an answer for how both of these things.
Okay, on the QUBO, I answered it here with a calculation here, the noise and the noise free. In the machine learning, it's actually much less sensitive because it depends what is key on the machine learning, that the learning happens as a function of the phase of matter, and phases of matter are robust. So the system learns very well when it's in the many-body localized phase, in the localized phase, and the phases, if you change a little bit locally, the couplings or the disorder or the dissipation T1 and T2 times, you still stay on the same phase. That's what is interesting here. So the numerics show that we are at least 10 to 100 or maybe more or 1,000 times more robust depending to what is out there, because you don't need in digital quantum computing, the gate error accumulates, and after a while you just lose it. It's not connected to the phase of the matter.
Okay, let's see. I cannot see any more questions at the moment.
I have a question, actually. So can you hear me, Dimitris?
Yes.
So with many-body localization, I saw in one of your earlier slides that you had all of the states localized on individual lattice points. But in localization theory more generally, you can have an Anderson type localization that arises from multiple scattering and interference rather
They
than...
were not in, that was a semantic thing. They are not localized in its state. Sorry, if that was what's showing here. You mean this one?
Yes.
Yeah, that's just...
Okay,
go on.
Yeah, so in many-body localization, you are talking about a localization that doesn't arise just from there being a particularly deep
No, exactly. The interaction versus disorder here, U is compared with J is 3.5 Actually, if we go to the phase diagram, so this one is done on a U, which is around 4 times the hopping. That's why you get this. So if you had only non-interacting case, it would be a flat. So as soon as you hit this delta equals 2, this is an incommensurate. I don't have the Hamiltonian here. I skipped it. We put some disorder here that this kind of, without the U, this model is predicted to have a phase transition at delta equals 2, a sharp one. So anything below.
So your omega n there is how does that compare with U in your calculations, or
So
the distribution?
Here, what the U does basically creates this, some of the states shift, so they go in. So for example, the states here, this is left is the extending the qubit lattice, and right is in the energy space. So this is the energy spectrum, like 49 Engel states here. So in the middle of the spectrum, you see they are, because of the interaction in this case, that's kind of few body localization. There's only 2 or 3 particles, but we can call it many body signatures. The states here in the middle, change phase. They don't change at 2 as before. The edges go down and the middle goes up, basically. If you make the U smaller, this gets flatter, and then U equals 0. This is completely red below 2 and completely blue above 2. So it's the interaction that makes this this curving of the edge.
So the other question I have, which comes from many years ago, was it was always said that one couldn't see Anderson localization with photons. So presumably, if you can't,
yes, yes, that's a good point. These are interacting photons. It's different. So it's like a strongly interacting particles. They have a U. They have I mean, you try to put one in, like photon blockade, the cavity QED, and it bounces out, and that's what we are doing here, basically.
Right, interesting.
They are photon-like bosonic excitations. They are not normal photons like in the user context.
Yeah, because I mean, I did my PhD with John Pendry, and there was a lot of discussion of this sort of thing and how one might see Anderson localization in photonic systems.
Yeah.
Anyway, yes, good. Oh, fantastic, interesting talk. Thanks very much.
Thank you for inviting me, and it was great to virtually see some of the Cambridge crowd again. And feel free to drop me a line. I'm happy to. If people want to follow up, we can discuss, or I can talk to members of my group. And do note the open positions. We are looking for good people that want to leave the cold of England and come to the equator.
I was actually thinking during the talk that your talk could really actually be a lecture course. That an hour doesn't really do justice to so many different subjects.
That was sorry for squeezing too much. I hope it was not too overloading. But
no, not at all. No, very interesting.
Thank you.
Just see one final question before we just quickly from Charles Smith here. He says that many body localization is very sensitive to the type of disorder. Is this well defined with just 9 qubits?
Well, obviously, no. This is a finite size system, and we see the finite size effects. Let me see if I have the. I think I saw this. That's a very good question. This is disorder on the local frequencies on the oscillators. When we also did level statistics, and then we saw the finite size effects, but I don't have the slide here. Let me see if I have it here, where we see that as you hit the sides of the lattice, the statistics don't go as you. I don't have it now. Definitely, the finite size of the lattice is there, but the fact that we could do full spectroscopy, and we could analyze, and they could, we could see everyone I mean, there were only 49 here, but we could actually probe them one by one and see the participation ratios. It was an interesting thing. This was something that was not possible to do in larger systems. So that's kind of the trade-off. Of course, now this was nine sites. There was 4 years ago. Now they have 53. We hope they will be interested to do some of this physics there now and not only do, supremacy or other things. But it's definitely an interesting question. The finite size effects.
Okay, thanks so much, Dimitris. This was really great to hear about all the kind of exciting things going on in your groups.
Thank you.